Good morning, everybody. Okay, today's topic will be on chapter 14, electrostatic. Okay, electrostatic is one of the topic that is quite simple, but yet is quite difficult to score in exam because students tend to leave out certain keywords when they're answering the questions when you're looking at the concept. Okay. In the next few minutes, I will run through the basics of the theory about the electrostatics and some of the keywords that students will need to take note. Okay, here we go. Now, for electrostatic, okay. Now, for electrostatics, it has two sections in this topic, 14.1 and 14.2. Okay, 14.1 will touch base with the basics. What are the common phenomenons that we have when we look at electrostatics and what are the various components. Electric field 14.2 look at how the phenomenons or the properties are being uh, manifested on maybe in terms of electric field, and to look at how it's been drawn or how it's being interpreted on the paper scale. Okay. Now, electrostatics, okay, in general, electrostatics it revolve around when we look at electrons. Okay, because electrons are free to move around, uh, add or remove from the object. So what happens is in the actual case is that what happens is that in reality, most of the atoms are neutral. Okay, so when they're neutral, we are saying that the proton and the electrons, they are of equal number. Okay, so the plus and minus are equal. So in the sense that they will actually be balanced, they will be able to offset each other. But what happens is when your electrons are removed or added. Okay, let's say if my electrons are removed, okay, which means that if my electron is removed, you simplify that the atom itself is actually lacking of electrons. So as a result, means the overall charges in the system will be like I will have more positive charges as compared to a negative charge. So I would say that the atoms will be now become a positively charged particle. The reverse will also happen. What happens if I have additional electrons being added now? So which means now that my electrons will be more than my my proton, the positive charges. So the overall net charge for this atom will be positive charge. So it's negative charge. So I would say the atoms will be negatively charged. Okay, so in the nutshell, we are looking at is like we have three different situations whereby you have neutral, whereby the proton and electrons are actually the same number, and I will have a electrons which is more than that, which means the particle will be negatively charged. The other extremes whereby the electrons are lesser than the proton, which means the overall charge will be positively charged. Okay, so these are the three things that we really need to take note before we start electrostatics, because electrostatics generally revolve around positive and negative charges. Okay, one of the phenomenon that we have is that the light charge repel means plus and plus will repel. Likewise, unlike charge, it means that plus and minus the different charges, they will actually move towards each other. Unlike charge, usually we have another name for it. We just tend to write opposite charge. Okay, like charge usually here refer to plus, okay, and plus, or we have minus and minus. Okay, so like charge, it could be positive or positive charge or negative charge. Okay, so they will tend to repel each other. Unlike charge, they will attract each other. Keywords that we are looking for is this the highlighted in red and the red box. Okay, these are the keywords that we look at to explain certain phenomena. So here what we have is in general, you will find that the charges when the actions, the phenomena, what happens is when I have maybe two object, they are maybe light charge, positively charged and positive charge. So what I do is when I bring them near to each other, you'll find that they will actually fly away from each other, or what we call repel. So when you look at the explanation between that, you have to remember that you have to write the keywords light charge repel, and therefore the objects are actually moving away from each other, not just looking at like all the object move away because they are the same charge. Okay, you have to use the keywords like light charge repel, or sometimes you have to use the word unlight charge attracts to symbolize the motion, the forces. Now, charges in general, for charges at O level at this junction now, we don't really deal with much charges calculations. Okay, so but we still need to look at the SI unit for charges is in coulomb, which is capital C. Okay, the charge by electrons is 1.6 times 10 or minus 19 coulomb. Okay, usually we have a minus sign, but we just tend to ignore it because we know that electrons is actually negatively charged. So the charge is actually symbolized by negative 1.6 times 10 to the power minus 19 charge. So sometimes we just leave off the negative sign because we already mentioned it's the electrons. If it's proton, okay, proton and proton, okay, it will be the same. It will be positive. One proton, okay, one proton, one single proton, the charge will be 1.6 times 10 to the power minus 19. Okay, sometimes we also don't write positive charge because we know that it's already a proton. The inherent charge will be positive. Okay, so now when you have, when you look at electrons, which you have, if you have one charge, okay, 1 coulomb charge, okay, how many electrons are we looking at in 1 coulomb charge? Okay, if one electron is 1.6 times 10 to the minus 19, 1 coulomb charge, you effectively you have like 6.25 times 10 to the power 18 electrons. That's like a lot of electrons in just a single particle charge. Okay. Now with this, okay, this will, like, in general, the electrostatics, if you look at the basic of this, we are looking at positive charge versus negative charge. There are two different charges that exist. And what are the actions, or what we say, what are the keywords that we are looking at? Okay, here keywords we mentioned here is light charge attract, light charges attract, unlike charges repel. Okay, light charge repel, unlike charge attract. Sorry. Okay, so this is the keyword that we're looking for. Okay, whereby it will symbolize the phenomenon or the question's observations. Okay, you, in the stating answer, you have to include this, either one of these, inside your answer. Okay, the other thing that we look at is how do we present this electric charge, or we know that plus and minus, they will plus and minus, unlike charge, they will attract. But I would like to, but we would like to know where is the area of influence, where will I actually feel the effect of the force, the attractions, or where will I feel the effects of repulsions, and that's where it brings us to the electric field section. Okay, electric field, okay, is what we mean by electric force is the force that we look at, whereby it's repulsion or attraction. Okay, now, these forces are what we call non-contact force, meaning the plus and minus, unlike charge, when you bring them near together, they will just fly towards each other because of attraction, but nobody is actually pushing them. Same thing if it's unlike charge, when you look at repulsions, okay, you don't really need them to be touching each other to have that repulsion force. Okay, so when we talk about these forces being experienced, we also look at where are the forces, where do you experience this force, or the region whereby I experience this force. Okay, and the region that we experience this force, that region is, we have a term for it which we call electric field. Okay, so electric field is the area whereby I actually have or experience the forces. It could be attraction or it could be repulsions. Okay, now, so try not to use these words interchangeable because they means differently. Electric field actually usually symbolize the locations where I feel the force. Electric force usually refer to the action of the okay, whether of the charges. Now, in electric field, how do I represent the area, the regions? Okay, it's usually by field lines, and the field lines have certain criteria. Okay, the field lines are actually, you have the field lines, they are actually dictated by, indicated by arrowhead, and sometimes even the field line itself. Okay, the location or the placement of the field lines, the placement, whether they are near to each other or they are further from each other, it does make a difference. Okay, we'll look at it later on. Okay, now for arrowhead here, the direction of field lines, we have a way of getting it, or we have a way of indicating it, is whereby it's in the direction of a positive charge. Okay, the field line directions, or the directions whereby indicate the field line, is dictated by the positive charge, a small positive charge. How do we look at it? Is example this. Okay, so if I have a positive charge here, how do I draw the electric field? How am I going to draw the electric field of this positive charge here? How am I going to draw it? So what I do is I actually use a small test charge, which are positive in nature. Okay, this is by convention. So what I do is I place, like, I have a positive charge here. So what I do is I place a small positive charge here. So let's say I place a small positive charge. I bring it near to it. Then after that, I let go. So what I do is when I let go, this small positive charge will actually move in a certain directions. So what I do is I will actually note down directions, I will detect it, I will actually draw it. Then what I do is I repeat the experiment for different locations using the same positive charge. Then after that, I let go, I will detect, I'll remember the movement directions. And that movement direction will actually tell us where is the electric field. Okay, so in the sense that you look at it, you'll find that the positive charge, okay, if I bring a small positive charge, the test charge here, okay, if I bring a small test charge here, okay, if I bring this small test charge near to the positive charge here, what it does is that, give me a minute, okay, when I bring this test charge near to him and I let go, you'll find that this positive charge will actually move in this direction. So I will record this direction down, okay. Then what I do is I will go to another location, I bring the same test charge, I will bring it near to the object. So what do I do now is I let go, and you'll find that this test charge will actually move outwards. Why it move outwards? Okay, one of the criteria is why it move outward. Remember the keywords. Okay, why I move is because light charge repels. Okay, so same thing. If I put a test charge here, I bring it near to the positive test charge, and I let go. And you'll find that this positive test charge will actually move in the directions dictated by light charge repel. So you'll move to the left. So what I do now is I bring this test charge to every corner. You'll find that this will be the outcome. Okay, these will be the few lines that I'm talking about. Okay, this will be the few lines that I'm talking about. And this is how the few line of a positive test charge will look like. Okay, this arrow is dictated by the small test charge that I'm using. So what do I do is, if I have multiple plus and minus, okay, so I will repeat the same thing. Okay, the other scenario is also the same. If I have a negative test charge, let's say if I have a negative test charge now, so if I have a negative charge, how do I know where is the electric field? What I do is I will take a positive test charge, I'll bring it near to the electric field. So I bring it near, okay, after I let go. So the moment I let go, you'll find that this positive test charge will actually fly towards the negative charge. Why? Because unlike charge attracts. Okay, so what I do now, I will have another test charge. I bring the test charge to another location, let's say here, positive test charge. After that, I let go. You'll find that the positive test charge will fly to the negative charge. Okay, because unlike charge attracts, and if I do it for different location, you'll find that I will have multiple arrows, all having one same pattern whereby it points towards the negative charge. You'll fly towards the negative charge because unlike charge attracts. So eventually, if you do it for multiple locations, you will find that the electric field for negative test charge will look the opposites as a positive test charge. Okay, so instead of, you will look the same, but instead of going out like the positive test charge, negative charge particle, the electric field line will actually be pointing towards the charge itself. Okay, so for negative test charge, it looks the field line will be pointing towards. Okay, for negative charge, the field line will be towards. For positive charge, the field line will be going outwards. Okay, usually the layout looks the same, but just the difference in directions. Same thing. Okay, what do I do when what will happen when I have a plus and minus when they interact together? Let's take a look. Okay. Okay, so now what do I do with this? Now, if I have a positive and negative test charge, okay, same thing. How do I indicate the direction? If I will take a positive charge, and I put here, you'll find that it will be repelled this way. So if I do this for a couple of times, you will find that the electric field of a plus and minus, when it go together, it actually follows a certain pattern. For example, if I have a positive test charge here, you'll find that plus and plus, they'll repel and you'll be pushed to the right. And when the positive test charge is moving to the right, the positive test charge and the negative test charge, opposite charge, the positive test charge and the negative charge, okay, they will attract each other because unlike charge attracts. So you'll find that my positive test charge will actually move from the left to the right this way. So this is how I get the direction. And similarly, if I put the positive test charge here, plus and plus, they'll repel because they are light charge. They repel. Then when the test charge is somewhere here, positive test charge, negative charge, unlike charge, they will actually attract. So you will have a series of field line curling from plus to minus. Okay. And this is what we mean by the final outcome of the field lines. Okay, remember same thing, positive charge, the arrow, the field line arrow is always from the positive to the negative charge. Okay, now in general, the field lines like depends on the teachers. We usually tell you guys to draw like maybe a balanced field line, whereby there's a field like what we call a line of symmetry. You take a look, the line of symmetry is like this way. Okay, we always try to ask you all to draw the balanced field line whereby the left side, right side all have equal number of field lines. Okay, so in general, try to draw the field lines. Okay, and there are certain pattern to it. Okay, so for example, the field lines. Okay, the field lines, what does it mean? Okay, they will always indicate the closer the field line, the stronger is the field strength. Okay, so which means the effect, the repulsion force will actually be stronger when it's nearer to the charges itself, or the attraction force will actually be stronger when it's nearer. And how when it's nearer, what do I indicate? I will draw the field line them to be side by side. Okay, same thing if far away means it will be weaker. Okay, exact field lines you can look up the textbook. You will have more examples, or you can look for teachers to just get a rough idea of how the field lines are drawn. Okay, parallel plate, it will be plus or minus, fairly straightforward, plus or minus. Okay, then after that, this is what we call uniform. It's uniform meaning that the in the middle is roughly is uniform. Okay, but you find that the side will be curved outwards. Okay, because the field line on the bottom and the last two, they will be like repelling against each other. So you have this curving here. So for parallel plate, remember, okay, because of its external, okay, and also there's earth field lines outside attracting it. The outside, the top and the bottom, they will turn to curve outwards a bit. Okay, but other than that, in the middle section, this area, the field line is actually more or less uniform. They will roughly have the same strength. Okay. Now with this will be the last section of the of the electric field. So in that, it's a very short topic whereby we look at the field line, the electric charges plus and minus. After we look at the keywords. Okay, so we have the keywords at the first sections. Okay, take note of it. And after that, you have the drawings. Okay, for the electric field lines. Okay, electric fields. Okay, of different combination of maybe positive charge or negative charge, and sometimes we have plus and minus charge together. So you just need to take a look at the field lines. In necessary, sometimes I may ask you to draw. So take note of the drawing and the arrows. Okay, with this, okay, if you have any comments, okay, just if any questions, just leave your questions or comments at the comment bar below. Okay, if not, okay, remember to subscribe to my channel to look at for the latest update for different topics that is upgoing. Okay, thank you very much, and that's all, folks.